Have you ever noticed how sound kind of like acts differently in different places? Like,
Mhm.
when you're up on a freezing mountain and everything sounds so crisp and sharp,
Yeah,
compared to, say, a humid day at the beach where sounds seem a bit more, well, mellow.
right. Almost muffled.
It makes you wonder if sound itself changes depending on its surroundings.
It's a great observation, and it's exactly the kind of thing we are going to explore today as we take a deep dive into the world of sound waves.
We are going beyond simply hearing and into the nitty-gritty of how sound waves are actually made, how they travel, how they behave, and maybe even some surprising ways they interact with the world around us.
Absolutely. And to do that, we'll be drawing on some solid scientific explanations of what are called mechanical waves. Specifically, we'll be focusing on longitudinal sound waves, which are the kind that travel through things we are all familiar with, air and water.
Our mission today is to give you a really clear and thorough understanding of these fascinating waves. We'll be covering all the key theories and concepts behind them.
Right, and we'll even touch on some real-world research and examples to show you how this all plays out in practice.
We'll break down any jargon, compare different perspectives, and by the end of this, you'll have a solid grasp of how sound waves work and why they matter.
Let's start with the basics. What exactly is a sound wave? At its most fundamental level, a sound wave is a longitudinal mechanical wave.
Okay, that sounds a little technical.
It's basically a disturbance that travels through a medium, most commonly the air around us, and it travels in a very specific way. The particles in the medium, like air molecules, vibrate back and forth in the same direction that the wave is traveling.
So it's not like little packets of sound are shooting out from my mouth to your ear when I speak.
Not exactly. It's more like a chain reaction. When I speak, my vocal cords vibrate, causing the air molecules right next to them to vibrate.
Hmm.
Then those vibrating molecules bump into their neighbors, causing them to vibrate, and so on.
So the vibrations travel outwards, kind of like a domino effect.
Exactly. And what our ears actually detect are these tiny, rapid changes in pressure that are created by those vibrating air molecules. These pressure fluctuations are what we perceive as sound.
I've heard sound described in terms of both the movement of these particles, what you call displacement, and those pressure fluctuations. Are these two different ways of looking at the same thing?
You're absolutely right. They are definitely connected. For a very simple sound wave that looks like a smooth sine wave, the displacement of the air molecules and the pressure fluctuations don't actually happen at the same time. They're slightly out of sync.
Out of sync.
Yeah, what we call out of phase. Imagine a sound wave as a series of peaks and valleys. The point where the air molecules are squeezed together the most, that's a peak of pressure.
Oh,
But right at that same point, the particles themselves are momentarily not moving.
oh.
And then a quarter of a cycle later, when the particles are moving the fastest, the pressure is actually back at its normal level.
So it's a continuous back and forth,
Right?
but pressure and displacement are always a little bit off from each other.
Exactly. It's a bit like a dance between pressure and displacement, with each one taking the lead at different points in the wave.
Okay, that's a cool way to think about it.
Right.
So how do we actually go from those tiny movements of air molecules to the pressure changes that we hear as sound?
You can visualize this pretty easily. Imagine a tiny cylinder of air.
Okay.
When a sound wave passes through it, one end of the cylinder gets a little push.
Uh-huh.
Now, if the particles inside that cylinder spread out, the volume of that cylinder increases and the pressure inside decreases.
Makes sense.
Conversely, if you squeeze those particles together, the volume decreases and the pressure increases. It's like squeezing a balloon.
So the pressure fluctuation, that change in pressure, is what we actually hear as sound.
That's it. And we can actually represent this pressure change mathematically.
I'm not a huge fan of math, but I'm willing to give it a try.
We use the symbol P to represent pressure, and we can write it as Pxt, meaning the pressure at a specific point x and at a specific time t.
Okay, that makes sense.
And the pressure fluctuation, the amount that the pressure changes from its normal level, is usually labeled as APE.
So we're talking about how much higher or lower the pressure is than the normal atmospheric pressure we usually experience.
Exactly. And as you might have guessed, there's a whole bunch of fascinating math involved in describing how those pressure changes propagate through the air and create the sounds we hear.
I bet there are some pretty gnarly equations involved.
You're right. But the cool thing is that these equations actually help us understand how different properties of the sound wave, like its frequency, amplitude, and speed, are all connected.
Maybe we can touch on some of those key equations a little later.
For sure. But first, let's talk about the two main things we perceive when we hear a sound: loudness and pitch.
Okay, I think I have a pretty good intuitive understanding of those.
You probably do. But diving a little deeper reveals how these subjective experiences are actually linked to the physical characteristics of the sound wave itself.
So louder sounds have bigger pressure fluctuations.
You got it. The larger the pressure change, the louder we perceive the sound to be. But it's not a perfectly linear relationship.
What do you mean?
Well, our ears aren't equally sensitive to all frequencies of sound. For example, we need a much larger pressure change to hear a low-frequency sound at 200 hertz, or a really high-frequency sound at 15,000 hertz, as being the same loudness as a sound at, say, 1,000 hertz, which is right in the middle of our hearing range.
So that's why those really deep bass notes or super high-pitched whistles sometimes sound quieter, even though they might actually have the same intensity on a sound meter.
That's exactly right. It's all about how our ears are tuned to different frequencies.
Okay, and what about pitch? That's
Right.
basically how high or low a sound is, right?
Precisely. And pitch is primarily determined by the frequency of the sound wave. Higher frequency means more vibrations per second, which we hear as a higher pitch. Think about the difference between a deep bass note and a high-pitched flute.
The flute has a much faster vibration.
Exactly. And while pressure amplitude, that size of the pressure change, mainly affects loudness, it can have a small effect on pitch too.
Really?
Yeah, there's some evidence that suggests a sound wave with a larger pressure amplitude might be perceived as being very slightly lower in pitch, even if it has the same frequency as a quieter sound.
Oh, that's interesting. I never would guess that. Now, what happens to these characteristics, the frequency, amplitude, and all that, when a sound wave travels from one medium to another, like from air into water, or from water into a solid material?
This is a really important point. The frequency of a sound wave actually stays the same when it travels from one medium to another.
Hmm. Why is that?
Think of it like tapping a drum. If you tap it once per second in the air, and then submerge that drum in water and tap it at the same rate, you're still tapping it once per second.
So the frequency, the rate of the vibrations, is set by the source, not by the material the sound is traveling through.
Precisely. However, the speed of the sound wave can change dramatically depending on the medium.
Ah, so that's why we see lightning before we hear the thunder. Light travels much faster than sound.
Exactly. And because the speed of sound is different in different media, the wavelength of the sound wave, that's the distance between two peaks of the wave, will also change.
So a sound with a certain frequency might have a short wavelength in air, but a much longer wavelength in water.
Exactly. And the amplitude of the sound wave, both the displacement amplitude and the pressure amplitude, can also change when it crosses from one medium to another. This is because some of the wave's energy might be reflected back at the boundary between the two media.
So it's kind of like a sound wave hitting a wall and some of it bouncing back.
Precisely. Some of the energy is reflected and some is transmitted into the new medium.
Fascinating. We hear lots of different types of sounds all the time. What's the difference between, say, a musical tone and just random noise?
That's another great caution. Musical tones, like the notes you hear when someone plays a piano or a guitar, are created by very regular repeating vibrations.
Huh?
These sounds can be represented by a wave that has a specific frequency and a pattern of overtones, also called harmonics, which are multiples of that fundamental frequency.
So a musical tone is basically a neat, organized set of frequencies.
Precisely. Noise, on the other hand, is much more chaotic and random. It's a jumble of different frequencies that don't have that nice harmonic relationship.
Like the sound of static on a radio.
Exactly. That's a good example of noise. Or the sound of wind rushing through trees, or the sizzle of a frying pan.
Those are all very complex sounds.
Right. Another interesting example is something called white noise.
White noise, I've heard of that. It's supposed to be good for sleep, right?
Some people find it helpful, yeah. White noise is interesting because it contains all audible frequencies at roughly equal intensity.
So it's kind of the ultimate mix of sound.
Exactly. And while it might sound random, it can actually be helpful in masking other sounds and creating a more calming auditory environment.
We've talked about how we perceive sound as loudness and pitch. But what about the actual power of a sound wave, the energy it carries?
That's where the concept of sound intensity comes in.
Okay, so how do we measure this sound intensity?
Sound intensity, denoted by the letter I, is defined as the amount of energy a sound wave carries per unit area per second.
So it's a measure of how much sound energy is flowing through a given area in a given time.
You got it. And we usually measure sound intensity in watts per square meter, which is a unit of power per unit area.
What's the relationship between the intensity of a sound wave and its amplitude, that maximum displacement we talked about earlier?
They're definitely related. The intensity of a sound wave is proportional to the square of its amplitude.
Square of the amplitude.
Yeah, that means that if you double the amplitude of a sound wave, its intensity increases by a factor of 4.
So even small changes in amplitude can lead to big changes in intensity.
Precisely. And this explains why loud sounds can be so much more damaging to our hearing than quiet sounds.
Makes sense? They're carrying a lot more energy.
Exactly.
So how much power are we talking about for everyday sounds? Like, how intense is a normal conversation?
You might be surprised to learn that the sound power of everyday sounds is actually pretty small.
Really?
Yeah, a typical conversation only generates around 10 microwatts of power.
10 microwatts.
That's 10 to the power of -5 watts. It's incredibly tiny. Even a loud shout might only produce about 30 milliwatts.
Wow. That's way less than I thought.
And to put that in perspective, if every single person in New York City was talking at the same time, their combined sound power would only be around 100 watts.
That's crazy.
Isn't it? But when we are dealing with really loud sounds, like a concert or a jet engine, those intensities can obviously get much higher.
So how do we manage these huge ranges in sound intensity? I imagine it gets a bit tricky to work with numbers that go from microwatts to, well, whatever a jet engine produces.
That's where the decibel scale comes in.
The decibels, or dB. I have heard of those, but I'm not really sure what they mean.
The decibel scale is a logarithmic scale, which means it compresses a huge range of values into a smaller, more manageable scale. Instead of dealing with those tiny numbers, we can talk about sound levels in decibels.
Okay, so how does that work?
It's based on a ratio. We take the intensity of the sound we are interested in, and we divide it by a reference intensity, which is the quietest sound a typical human ear can hear.
That's like a baseline for comparison.
Exactly. Then we take the logarithm of that ratio and multiply it by 10.
And that gives us the sound level in decibels.
Precisely. And because it's a logarithmic scale, every increase of 10 dB represents a 10-fold increase in sound intensity.
So a sound at 20 dB is 10 times more intense than a sound at 10 dB.
Exactly. And a sound at 30 dB is 100 times more intense than a sound at 10 dB.
Wow. That makes it much easier to compare sound levels. What are some typical dB levels for common sounds?
A very quiet room might be around 20 dB. Normal conversation is usually between 60 and 70 dB.
Okay.
A busy city street might be around 80 to 90 dB, and a rock concert can easily reach 110 dBs or more.
That's loud.
It is. And prolonged exposure to sounds above 85 dB can actually damage your hearing.
Yikes. That's definitely something to be aware of. Now, I'm curious, what happens when we have sound waves from different sources interacting with each other? Like when two people are talking at the same time, or when music is playing from multiple speakers?
That's when we get into the realm of interference, which is a really fascinating concept.
Okay, what is interference?
Interference happens when two or more sound waves meet at the same point in space. When this happens, the waves can either add together or cancel each other out.
They can cancel each other out. How does that work?
It's all about the relative positions of the peaks and valleys of the waves. If the peaks of one wave line up with the peaks of the other, they reinforce each other, creating a louder sound.
Okay.
This is called constructive interference.
Like when two waves team up to make a bigger wave.
Exactly. But if a peak of one wave lines up with a valley of another wave, they cancel each other out, and the sound is quieter.
So it's kind of like a wave tug of war, where sometimes they work together and sometimes they work against each other.
That's a great analogy. And this cancellation is called destructive interference.
So interference can make sounds either louder or quieter depending on how the waves align.
That's right. And a really cool example of interference is something called standing waves.
Standing waves.
Imagine a sound wave trapped inside a tube, like a flute or an organ pipe. The wave bounces back and forth between the ends of the tube, and if the conditions are right, it can interfere with itself in a way that creates a stationary pattern.
A stationary pattern.
Yeah, there are specific points along the tube where the air molecules are always still.
They don't move at all.
Nope. These points are called nodes.
Okay.
And then there are other points where the air molecules are vibrating with the maximum amplitude.
So it's like a wave that's frozen in place with some parts stationary and some parts moving a lot.
Exactly. That's a standing wave.
And these standing waves are what create the specific notes we hear from musical instruments.
Exactly. The length and shape of the instrument determine the wavelengths of the standing waves that can form inside it, and that's what creates the specific frequencies and therefore the pitches of the notes.
So a flute makes different notes than a clarinet because they have different shapes and lengths, which create different standing waves.
That's right. And another factor that affects the pitch of wind instruments is the temperature of the air inside them.
How does temperature come into play?
Well, we know that the speed of sound in air depends on the temperature.
Right, we talked about that earlier.
As the air gets warmer, the sound waves travel faster.
Okay.
Now, when the speed of sound changes, the wavelengths of the standing waves inside the instrument also change.
Uh-huh.
And since frequency is related to wavelength and the speed of sound, the frequency of the notes also changes, which is what we perceive as a change in pitch.
So warmer air means a higher pitch. That's why musicians often need to warm up their instruments before they start playing.
Exactly. They need to get the air inside the instrument to the right temperature so that it's in tune.
Makes sense.
And this whole concept of something vibrating at its natural frequencies is called resonance.
Resonance.
It's what happens when you push a swing at just the right time to make it go higher.
Or when you sing a certain note and a wine glass starts to vibrate.
Exactly. When you apply a force to an object at its resonant frequency, you get a huge increase in the amplitude of the vibration.
So it's like giving the object a little nudge at just the right moment to make it shake like crazy.
Exactly. And resonance plays a big role in music and even in our own hearing.
Tell me more about that.
Well, musical instruments are designed to resonate at specific frequencies, which creates the notes we hear. And our own ear canals actually resonate at a certain frequency too, which helps amplify the sounds in that range.
Wow. So resonance is everywhere. Now, what about the Doppler effect? That's the thing that makes a siren sound higher pitched when it's approaching you and lower pitched when it's moving away.
You got it. The Doppler effect is named after Christian Doppler, a scientist who studied how the motion of a source or an observer can change the perceived frequency of a wave. It happens with all kinds of waves, not just sound waves.
So light can also be Doppler shifted.
Absolutely. The light from distant galaxies, for example, can be shifted towards the red end of the spectrum, which tells us that those galaxies are moving away from us.
Wow, that's pretty mind-blowing.
Yeah.
Well, let's get back to sound.
Sure.
How does the Doppler effect actually work with sound?
Imagine a car with a siren moving towards you.
Okay.
As the car moves forward, the sound waves it emits in front of it get compressed. Because the waves are squeezed closer together, the distance between them, that's the wavelength, gets shorter.
Right.
And since the speed of sound is constant, a shorter wavelength means a higher frequency.
So that's why the siren sounds higher pitched when it's coming towards you.
Exactly. And as the car passes you and moves away, the sound waves behind it get stretched out, resulting in a longer wavelength and a lower frequency.
So that's why the pitch drops.
You got it. And the amount of the frequency shift depends on how fast the source is moving relative to the listener.
So a car speeding past you would have a bigger Doppler shift than a car moving slowly.
Absolutely.
Okay, that makes sense. Now, we can't end this deep dive without talking about shock waves and sonic booms.
Right. Shock waves are a pretty incredible phenomenon. They happen when an object, like a supersonic jet, moves faster than the speed of sound.
I've heard that when a jet breaks the sound barrier, it creates a loud boom. Is that the shock wave?
That's exactly it. When an object moves faster than the speed of sound, it creates a cone-shaped pressure wave that trails behind it.
Like the wake of a boat.
Sort of, but the shock wave from a supersonic jet is a much more intense and sudden change in pressure. And when this shock wave reaches our ears on the ground, we hear it as a loud sonic boom.
So that boom isn't just a one-time thing that happens when the jet first breaks the sound barrier. It's a continuous wave trailing behind the jet.
Exactly. As long as the jet is moving faster than the speed of sound, it's constantly creating this shock wave.
Wow, that's amazing. It's like the jet is pushing the sound waves out of the way faster than they can travel, creating this buildup of pressure.
You got it.
So are shock waves only about loud noises, or do they have any practical applications?
Actually, shockwaves do have some surprising uses, particularly in medicine. For example, they are used in a procedure called lithotripsy to break up kidney stones.
How does that work?
Doctors use focused shockwaves to target and break down kidney stones into smaller pieces, which can then be passed naturally.
So it's like a non-invasive way to get rid of those painful stones.
Exactly. It's a much less invasive alternative to surgery.
That's amazing. Well, we've covered so much ground in this deep dive. We started with what sound waves are, how they're made, and how they travel. We talked about loudness, pitch, intensity, the decibel scale, interference, standing waves, resonance, the Doppler effect, and even shock waves.
Yeah, that's quite a list.
It's been a fantastic journey through the science of sound.
It really has.
To wrap up, maybe we can revisit that observation we started with. about how sound seems to behave differently in different environments.
Absolutely.
So why does sound seem so much crisper and sharper up on a cold mountain compared to a warm day at the beach?
As we've discussed, the speed of sound is affected by temperature. In colder air, sound travels slower,
Right.
and that slower speed can subtly affect how we perceive sounds, making them seem sharper and more distinct.
So even though we might not consciously realize it, the temperature of the air is constantly shaping our auditory experience.
That's exactly right, and it's a great example of how the physics of sound waves impacts the world around us in often unexpected ways.
Well, that's a perfect note to end on. Thank you so much for sharing your expertise and taking us on this incredible journey.
My pleasure.
I encourage all of our listeners to keep exploring the world of sound and to ponder those everyday phenomena that might reveal even deeper scientific wonders.
And as always, if you find yourself with more questions, don't hesitate to dive even further into the fascinating realm of acoustics. You never know what incredible insights you might uncover.
Thanks for joining us today. Until next time.